So we have a curve over here and we're basically trying to find the area under this curve. Now if you realize, you can see that the area under this curve is not a proper shape. It's a really weird looking shape. It's not a rectangle, it's not a triangle, it's not a circle, it's not a normal shape, so we can't use the normal formulas for areas to find out the area under this curve. However, what we can do is we can basically approximate the area under this curve using rectangles. And by adding these rectangles and then calculating their individual areas and then adding them up, we can basically get a close approximation to what the actual area under this curve is going to be. Now remember, that is not going to be an exact area, but it is going to be an approximation. Now each rectangle has a width, and that width is given to us by delta x. Delta x basically means the change in x. So if you look at each triangle has a right hand side and a left hand side. So if you subtract the x coordinate of their right hand side with the x coordinate of their left hand side, then you basically get this change in x, or this delta x, or what we know as the width of the rectangles. Now this time we have reduced the width of the rectangles, and what that has allowed us to do is again add in more rectangles. Now if we calculate the individual areas of all of these and then add them up, we're going to get an even closer approximation than before. But we want to get the exact area under this curve. So what we're going to do is we're going to reduce the width, or the delta x, to a really tiny amount. And let's see what that is going to look like. So right over here, we have these really small rectangles. Why? Because we've reduced their width a lot. This time they do exactly tell us the actual area under this curve. So if we find the individual areas of all of these rectangles and then add them up, we're actually going to get the area that is going to be under this curve. Each rectangle has a width. We call that width dx. Why dx? Well, because we've basically reduced the widths and we've made them so small that now the width is really tiny. And so we represent the tininess by dx. The symbol for tininess is d. That's why we use the dx over here, to denote that the width of the rectangles is really small. And so what's going to be the height of this rectangle? Well, if you realize, all of these rectangles are bounded by this curve. They cannot go over this curve or outside of this curve. So their heights are dependent by this curve. And so that's what their height is going to be. It's just going to be what the curve is, what the height of the curve is. So we can say that the height of every rectangle is basically the same as the curve, because they're bounded by the curve, or they're limited by the curve. And now what we can do is we can basically add the individual areas of all of these rectangles up, and then when we do that, we're basically going to get the actual area that's under this curve. But where do we want to find the area from? So we want to find the area from, let's say, x is equal to 0, or the origin, to x is equal to 5. And so between these two regions, we want to find the area that is going to be under this curve. But before we do that, what is the formula for the area of a rectangle? Well, we all know it's just length, or the height, multiplied by the width. That's the area of a rectangle. Well, in this case, the height of the rectangles is given to us by f of x, and the width is given to us by d of x. So we just multiply those things and we're going to get the area of the rectangle. But we don't want the area of the rectangle. We want to find the area of under this curve. So what do? Well, we need to sum. So we're going to write the sum, and we're going to denote the sum with an s. So this right over here is an s. It's a weird looking s, I know, but that's an s. It means sum. So sum of what? Well, sum of areas of these rectangles. And what's the formula for the area of a rectangle? Well, we just found that out. Okay, so we basically are going to sum the area of these rectangles, but from where to where? Well, we want the area from x is equal to 0 to x is equal to 5. And well done. You basically now know what integration is.